Hey, Logan, does my microphone work?
Yeah, I can hear you.
Okay, I think I fixed it because last class I was asking questions and talking, and I don't think anyone could hear me because no one responded, but yeah.
Yeah, well, at least it's working now.
Okay, so good afternoon, everyone. So let's first talk about the midterm. So today we will start lecture 4, and right after that we will have the first midterm exam. And currently I'm thinking of scheduling the midterm 1 to be on the 15th February. So 15th, that is the next month, Tuesday in the class. So we are here, and next Tuesday we will finish the lecture 4. And next Thursday we have a review lecture for the midterm 1. And after that, on the next Tuesday, on the 15th, we will have midterm 1, in both in class and over the Zoom. Okay, so for those of you who are taking this course offline, I mean by watching the recorded videos, I will send an email to you, and we can accommodate on this. And so the midterm is 1 hour 20 minutes. Let me see. Yeah, 1 hour 20 minutes, 5 problems plus 1 bonus problem, covers the first 4 lectures. And you can bring a 2-sided reference sheet. And no calculators allowed. So that's basically the setup of the midterm exam. So it is it will be no more difficult than the homework problems. So I think you can review the homework problems and also refer to the review lectures. That should be pretty enough for the midterm.
And are we doing this
Are there any
only in
questions?
class, or are we also able to
Sorry.
take it
Let me-
online?
Can you say that again?
Is this in class, or are we doing this online also?
We do it simultaneously. We do it in person plus IVC. So if
Okay,
you can take you can connect to this Zoom meeting with the video turned on. So that's the IVC format.
okay.
So as for that, I'm actually in another class during that same time. So I was wondering about this because I'm taking two classes that are at the exact same time this semester, which is
Oh.
why if I have to be present, then I'd have to, maybe work with you on getting a time that I could take it with you, or maybe over Zoom some other time.
Yes. If there's a conflict, then we can schedule a separate time.
All right, sounds good. Thank you.
Okay. Any other questions regarding the midterm? So if you are taking the midterm in person, it should be very clear. But if you are taking it over the Zoom, make sure you have the video turned on, and also you also need to upload the reference sheet with your exam paper to the Canvas. But if you are taking in person, you can just hand me your exam paper. That's all I need. Okay, one comment. Okay, yeah. So if you are taking over the Zoom, well, that's I will give you extra 15 minutes to submit to the Canvas system. Yeah, but make sure you have everything prepared so that you can hand in the submission as fast as possible. Okay, so that's for the midterm, and I guess we will start lecture 4. So we have talked about the LTI system, the linear system and time invariant system. Now, just a very quick review, right? For LTI system, so first of all, it's linear. It's linear. And linear means if a system is linear, it means that the following two processes are equivalent. You can first so you can first feed two signals to the system. Right, and then you get their corresponding outputs. And then you do a linear combination. So this is, you first feed the individual signals to the system, and after that, you linearly combine their outputs. Or if the system is linear, you can equivalently do the follows. You first combine these signals. Okay, we first do a linear combination of the signal, and then feed this linearly combined signal to the system. Then the corresponding output is the same. It's A times Y1 plus. Okay. So if the system is linear, then we can either do the linear combination on the output side or on the input side. And for time invariance, it's the same idea. Now, if a system is time invariant, you can either first feed the signal to the system first, and then on the output side, once you obtain the output, you can shift the output by a time shifting tau. For example, you can do time shifting. Or you can first do a time shifting on the input, and then feed this shifted input to the system. And the output you get will be the same. So this is time invariance. And for an LTI system, it satisfies both properties. Okay? It is linear and time invariant. And in this lecture, we will discuss this LTI system in more detail. We will show that for this LTI system, its input and output relationship can be fully understood through the operation of convolution. So we will introduce this convolution operator. Okay. So the first important concept that we will introduce for the LTI system is the so-called impulse response. So the impulse response is defined as the output of the system when the input is the impulse, is the impulse signal. So basically, let's consider an LTI system H. And then we feed this special impulse signal to the system. So this delta T is the input signal. And then we look at the output. So this delta T, once we feed to the system H, so the output is capital H delta T. So we define this output of the system as the impulse response. Because this intuitively, right, this HT is just the response of the system to the impulse signal. So we call it impulse response. So we always denote the impulse response of an LTI system as HT. Now, what is HT? HT is basically, feeding this impulse signal to the system H. And the output is called the impulse response. Okay, so this is a very simple definition, and it is very fundamental because it turns out the impulse response can be used to characterize the input and output relationship of LTI systems in a very fundamental way. And we can see that for this impulse response, the input is a very special signal. It's the impulse signal. And this is because we will see later that any signal can be represented by the impulse signal in a general way. So that's why here we use the impulse. We care about the response to the impulse signal, not the response to any other special signal. For example, the unit, we have introduced a lot of special signals like the unit step signal, all those type of special signals. But here, the impulse response is the most fundamental one. Okay, now once we have this definition, we immediately can obtain the following properties. Now, first of all, because the system is LTI, so it is time invariant. Now, since it's time invariant, then I know that if I feed delta t minus tau, if I feed this time shifted version of an impulse response, of an impulse signal to the system, then by the time invariance property of this system, the output will also be the shifted version of the original output. Right. So if I shift the impulse by tau, the output will be the same impulse response and also shifted by the same amount of time shift tau. So this is by the time invariance property, TI. Okay, so this figure illustrates this time invariance property, right? If we feed this delta t to the system H, suppose the impulse response looks like this. And then by the time invariance property, if the input is a shifted version, it's a shifted impulse signal, then the corresponding output will be a shifted version of the impulse response. Okay, so this is the time invariance property. And at the same time, the system is also linear. So by the linearity of the system, we immediately have the following properties. Now this is the due to the property of linearity. Now because the system is linear, so we know that if we feed a linear combination of two signals to the system, this is equivalent to feeding the individual input to the system first, and then do the same linear combination, right? So by linearity, we have this equation. So basically, whenever you see a linear combination of inputs, you can always exchange the linear combination with the system operator, capital H. So basically, this capital H, if you view capital H as a function, then it is a linear function in the input signals. And once we have this, so this linearity definition is defined for a pair of input signals. Based on this, we can extend this property to multiple signals. So instead, we can consider a linear combination of infinite number of input signals. So we define this as a summation. It's a weighted summation of multiple input signals, xit. Now this index I can be either finite or infinite. So if we feed this linear combination of infinite many input signals to the system, it is equivalent to first feed each input signal xi to the system, and then apply this linear combination operator. So this is called extended linearity. And we can further generalize this extended linearity property to integration instead of summation. Because in general, integration and summation, they are very similar. So we can look at this equation. Now on the left-hand side, the input is an integration of signals. This can be viewed as a linear combination of these time-shifted signals, xt minus tau. And this a tau corresponds to the linear combination coefficient in the above equation. So you can imagine that now the summation can be generalized to integration, and everything else is the same. And then by the linearity property of the system, we can first apply the system operator to every input signal first, and then apply the integration operator. Okay, so basically for a linear system, we can have these different types of extended linearity properties. And in the previous slides, we showed that for a time invariant system, we have this time invariance property. So if a system is LTI, it means it's both linear and time invariant. So the system will satisfy both of these properties. Okay. Now we want to characterize the input and output relationship of the, let's say, a continuous time LTI system. So here we are only given the impulse response. So we want to characterize the input, output of an LTI system. And we are only given the input signal. So given input, and given the impulse response. So we will show that given this input and the impulse response of the system, we can determine the output of this LTI system through the convolution operation. Now, let's derive this fundamental relation, input and output relation for the LTI system using all the mathematical backgrounds that we introduced in the previous lectures. So if you look at the system diagram, right, we are given this X, the input signal, and we know that H is an LTI system, so it is linear and time invariant. So we want to determine the output YT. So this is the question that we are looking at. Now, before we do that, we first recall a fundamental result that we introduced for the impulse signal. Now, in lecture 2, when we introduced the impulse signals, we showed that this equation holds for any signal xt. Right, so let me write it here. Any signal xt can be written in terms of the impulse signal in this way. Right, so the proof is very simple, right? we have done this in the lecture 2, because this is a product of a general signal x tau with a time shifted signal delta t minus tau. And by the product property of the impulse signals, this is equivalent to xt times delta t minus tau. So first of all, delta, the impulse is an even function. So I can add a negative sign inside for free. So delta t minus tau equals to delta tau minus t. And then x tau times delta tau minus t by the product property of the delta function in lecture 2. We can quickly go to lecture 2. That is on this slides. Now by this property, so this is exactly what we have here. So by this property, we can replace the signal ft by a constant value of the signal evaluated at a specific time, capital T. And this capital T is the time shift of this impulse signal. And going back to here, the time shift is this small t. So we can replace x tau by xt. And this becomes xt integration. Because the integration is over tau, so now xt is a constant. And we know that the integration over this impulse signal is exactly 1. So this shows. So this shows the equivalence between these two quantities. This is exactly this equation here. Okay. Now, what is the physical meaning of this equation? It means that we can express any signal xt by a linear combination of time shifted and weighted versions of impulse signals. If you look at the right-hand side, the signal we are looking at is delta t minus tau. So it's the delta t signal shifted by tau. And then we are varying this time shift tau over the entire range. And for any specific time shift tau, we will weight this shifted impulse signal by the corresponding magnitude of the signal of interest. So we can draw a picture to illustrate this idea. I suppose this is your signal xt. This is the left-hand side. Now, what the right-hand side corresponds to is the following figure. This may not be a rigorous figure, but it provides the key intuitions. So we basically we will generate infinitely many time-shifted versions of the impulse signals. So this is tau. Right. So if you look at a specific time shift tau, then this arrow would be the shifted impulse signal, delta t minus tau. And then for every delta t minus tau, we are scaling this impulse signal by the corresponding magnitude of your signal of interest. So basically, we are scaling this arrow corresponding to the magnitude of this signal at this tau at this point tau. And then we are integrating all these weighted and time shifted impulse signals over the entire time domain. So it's basically, and you can see that the envelope of all these time shifted and scaled impulse signals will form your underlying signal xt. So this is the intuitive picture, intuitive explanation, illustration for this equation. So that means every signal we can decompose it into infinitely many time-shifted impulse signals and time-shifted and magnitude scaled impulse signals in this way. Right. So in the end, we have this first. We can, for the input signal xt, we can use this equation to decompose it into impulse signals instead of looking at the signal itself. That's why for LTI systems, we introduced the impulse response, because first of all, every input signal can be decomposed into, can be related to the impulse signal in this way. Okay, so this equation is just a recharacterization of the input signal. Now we are going to feed this input signal to the system, and let's see what happens. We want to look at YT, right? The output of the system. And by definition, that is H applied to XT. But this is just the system equation of this LTI system. And first of all, we just obtained this recharacterization of the input. So let's plug it into this equation. So instead of having xt here, I have integration x tau delta t minus tau. Okay, again, this is just a plug in this equation. And then we can start it to look at this expression here. This looks very complicated. It is we know that H is an LTS system, so we can utilize its linearity and time invariance property. But if you look at the input, now the input signal is rewritten in a linear combination form. It's a linear combination of these time-shifted impulse signals. And the linear combination coefficient are these x tau, the signal values. So we can invoke the linearity, extended linearity of the system. And then we can exchange the order of this H and this integration operator. Okay, so by linearity, this equals to, we can first feed this individual impulse to the system and then do the linear combination. Right. So because the system is linear, so we know that we can exchange this integration with the system equation, system operator. Okay. Now, if you look at this expression, the system is now applied to the time-shifted impulse signal. And this is a very fundamental quantity that we just introduced. Right? So this is just the impulse response of the system. And here the impulse is a time shifted. It's a time shifted version of the impulse signal. So we can apply by the time invariance property, we know that the response to this time shifted impulse is a time shifted version of the impulse response signal. So by the time invariance property, this is just the impulse response ht shifted by tau. Right, because the impulse response is defined here. It's the response to the impulse signal delta t. So ht is the impulse response. So now, if we want to look at the response to this time-shifted impulse, by the time invariance property, we just need to shift the corresponding impulse response by tau. So this is exactly a shifted version of the impulse response. So this is the derivation here, summarized in on this slides. So in the end, we obtain an equation. We now show that the output of this LTI system YT can be written in this way. And if you look at this equation, it is very clear. The output only depends on your input signal x tau and the impulse response function of your system h. Which means that for the LTI system, once we are given the input signal x, and also if we know the impulse response of the system, then we can use this formula to calculate the output YT. And then for simplicity of the notation, now this is a very fundamental relation, characterization of the input and output relation of LTI systems. Given the input x and the impulse response is also a fundamental quantity associated with the system because it's a response of the system to a very specific signal, the impulse signal. But once we know the input and the impulse response, we can calculate this integration, and then we can analytically get the output of this LTI system. So we give this a very nice and very nice notation called convolution. And we use star to represent the convolution between x and h. So this is the formal definition. Right. So the first equation is what we derived by leveraging the linearity and the time invariance property of the system. So the output YT can be calculated from the input and the impulse response in this complicated way. And then we give it a very simple notation. It's x convolution with h. Now more precisely, given xt and ht, given the input signal and the impulse response signal of the LTI system, the output is given by the convolution between xt and ht. And this convolution is defined in this way. Make sure you don't mess up with the tau and t in this convolution formula, right? So it's xt convolution with ht is defined as x tau ht minus tau d tau. Okay, so we are integrating over tau, but the time variable here is actually the t, right? So the t, the output at time t is equal to this integration with this t. So we are integrating over tau. The triangle over the equal sign means that this is a definition. So we define this complicated integration as, we denote it as x star h. And this star means represents the convolution operator. So this is the definition of convolution. It is a very fundamental operator because we derive this from the input and output relationship of LTS system. It's a linear system, time invariance. This is the most simplest system that we can have in this world. So for this fundamental system, it turns out that the input and output can be characterized in this very elegant way. Although the convolution may look a little bit complicated at first time, but later we have many intuitive explanations of convolution. But this is what we derive from the linearity and time invariance of this system.
I have a question.
Yes.
If you like convolve, or if you use convolution on two signals, is there a relationship if one of those signals is linear and time invariant and the other one isn't? And or if they're both linear and time invariant, is there a relationship between that and the output?
So when we talk about linear and time invariant, we are always referring to systems, right? We never define a linear signal or time invariant signal. So those two terminologies are only for systems. So
Okay.
yeah, so this convolution is defined for any arbitrary two signals. If you give any x and any h, their convolution is defined in this way. You have to evaluate this integration.
Gotcha. Thank you.
Yeah. So what we have here is that for linear and time invariant systems, the input and output relationship can be characterized by the convolution. So the output is the convolution between the input and the impulse response of the system. It's very simple. Now here's an illustration of the graphical illustration of all these proofs. We can look at this figure from top to bottom, line by line. In the first line, we have this impulse signal, and we have this corresponding impulse response. So the first line shows that if we feed this standard impulse signal to the system, we will end up with this impulse response HT. And the second line shows that if we further shift this impulse signal to an arbitrary position, now this is a shifted version, And then the corresponding response to this signal, to this input, would be a shifted version of the impulse response. This is by the time invariance property of the system. And now the third figure and the third and fourth line means that when we feed an arbitrary signal xt to the system, we can first decompose the input signal as a linear combination of shifted impulse response impulse signals in this way, right? So we have all these impulse signals located everywhere, and each of them is scaled with regard to the magnitude of the input signal at that location. And then by the linearity of the property of the system, then the output can be characterized for each of these shifted and scaled impulse signal. It will generate a corresponding shifted and scaled impulse response. And then and then the superposition of all these impulse responses will form the output of the system. Right, so if you look at third line, the arrow, the shifted and the time scaled node, the shifted and the scaled impulse signal is this shadowed area. That signal will generate a corresponding response. And then each of these arrow will generate a corresponding response. It's shifted and scaled in a proper way. And then their superposition will form the output of the system. And this is exactly what we have in this convolution operator. So each of those shifted impulse response, each of those shifted delta signals are now become, on the output side, become a shifted impulse response. And then we scale this impulse response by a proper value of the input signal, and then we superposition them. Right? That corresponds to this picture. Each of those arrows become an impulse response, shifted and scaled impulse response, and then their summation gives the output. So this is this actually shows the simplicity of this LTS system. We can view every signal as a linear combination of impulse signals, and then we just need to understand the response to impulse signals. So that's why it is characterized by the convolution between the input and the impulse response. Okay, and convolution is similar but totally different from the multiplication in the number system. Like when we have two numbers, complex numbers, we can do their product. But here for convolution, the calculation is much more complicated. We have to follow this formula, calculate this integration. However, we can show that the convolution operator has the following fundamental properties that are similar to the multiplication operator in the number system. So it is commutative, meaning that any signal H1 convolution with H2 equals to H2 convolution with H1. So you can exchange the order. So basically, in this input and output equation, it doesn't matter you put X on the left-hand side or H on the left-hand side of the convolution operator. And we have these association properties. So you can, if you have taking convolution with multiple signals at the same time, you can do either two of them. You can do H2 and H3 first, or you can do H1 and H2 first. And also, if we are doing, if we are taking convolution between one signal and the sum of two other signals, we can do a distribution. Calculate the individual convolution first, and then take the sum. So in this sense, it is similar to multiplication. But the way we calculate each of these convolution, is totally different from multiplication. It is not pointwise multiplication. And the convolution has many properties that we can, so these properties is just can be proved by following the definition of convolution. I think we can go over them, and I will comment on the high level idea of the proof. So the first property is a very simple property. Any signal convolution with the impulse signal is itself. So in this sense, this impulse signal in the convolution system, the impulse signal serves as the number one in the the number system. Every number multiplied by one is itself. So this HT, any HT convolution with the impulse signal is the signal itself. And this is very simple to prove. We can just follow the definition of convolution. Now, be careful when you write down the convolution formula. Okay, always follow this formula. Is the first signal is h tau, and then times the second signal delta t minus tau tau. And now you have this product, a product between any signal h and impulse signal. So we can utilize that property. So this product is equivalent to ht delta t minus tau. And now the ht is a constant because we are integrating over tau, so it's just ht integration of delta. And we know that the integration of the impulse signal over the entire time domain gives 1. So this is ht. So this shows that convolution between ht and delta is just the signal itself. And the following properties are very extremely useful when we go to the Fourier transform part. So the second property is the delay property, which shows that if we know the convolution between x and h gives y, then the convolution between their time-shifted versions, so now x and h are shifted by tau1 and tau2 respectively. So this time-shifted, the convolution of this time-shifted version is basically equal to the original output, but now this output yt is shifted by the time shift is a summation of the time shifts of both inputs. Okay, so basically the time shift of both inputs will affect the time shift of the output. And I think I can comment on the proof idea here. So basically, we can first write down the convolution formula for this convolution. Okay, let's do this practice. go back to this convolution formula. So it's this now both of these two signals are shifted. So when you write down when you follow this convolution formula, is the first signal xt. Now replace t by tau. So it's x tau minus tau 1. But you can define this as a signal in t. So it's replacing t by tau, and then the second one is h. You are replacing t by t minus tau. So it's t minus tau 2 d tau. And then in order to relate this to the original convolution, we need to do a change of variable. So that is the basic idea here. So after doing a change of variable, so suppose we can define tau prime as tau minus tau 1. So we do a change of variable x tau prime. So now tau equals to tau prime plus tau 1. So it's h t minus tau prime plus tau 1. d tau prime. Okay. So simplify this. It's h t minus tau 1 minus tau 2 minus tau prime. Right. I'm just rearranging these terms. And now I can view this as this is a constant, fixed constant, because we are integrating over tau prime now. So if you compare this with the definition of convolution, right? So you can see that we have x tau ht minus tau. Here we have x tau prime h, this entire thing minus tau prime. So basically, this is the index of the output. Right? You can see the output is yt, and this small t is right here. But now instead of having a small t, we have t minus tau 1 minus tau 2. So by comparison, this will give us this small y evaluated at t minus tau 1 minus tau 2. So basically, this shows that if both of the inputs are delayed, then after taking convolution, the output will delayed by the delay in the output is the sum of the delays in the inputs. Okay, so this is a very important property for convolution. And the next property is the derivative property. In many situations, we are going to calculate the convolution such that one of the signals takes a derivative form. In this case, we can show that you can first calculate convolution and then take the derivative. Yeah. So I should say sometimes it's actually going from the right hand side to left hand side. So we need to calculate the derivative of a convolution. And then you realize that maybe the derivative of one of the signals is very simple. So you can first calculate that derivative. And then this derivative signal is very simple, so that the calculation of the convolution will be much simpler. For example, if this ht is a unit step function ut, then clearly the derivative of unit step is a impulse signal, and the impulse and then any signal taking convolution with the impulse is just the signal itself. So sometimes calculating the derivative first can simplify the calculation of the convolution. Okay, so these are all the properties of convolution operator. So I think later on we have some examples for calculating the convolution. Okay, so we'll go to that part later. So the next part is about we can, for LTS systems, we can categorize this system by looking at the impulse response. Now, before we have introduced, in the last lecture, we have introduced many categories of systems: causal systems, stability of systems, and so on. Now, for LTS systems, it turns out many of these properties can be identified by examining their impulse response functions. For example, when we talk about the memory of a system, if the system is LTI, then this system is memoryless. If the impulse response is if the impulse response is a impulse signal, it's a scaled version of the impulse signal. The intuition is that if the impulse response takes this form, then you can imagine if I feed any input xt to the system, right? If the impulse response is a constant times the impulse signal, if the impulse response of the LTS system takes this form, then if I feed any signal xt to the system, now I know the output is the convolution between the input xt and the impulse response. But now the impulse response takes this very special form. And we know that any signal convolution with this impulse signal is signal itself. So it's just k times xt. And you can see that the output only depends on the presence of the input. So that which means by definition, it is memoryless. Okay, so if this LTS system is memoryless, we can just, the impulse response must take this special form. And if an LTS system is invertible, it also has this property regarding the impulse response. So let's denote the inverse system of the LTS system. So let's denote the impulse response of the inverse system as H1. Then this and the impulse response of this system itself is HT. Then if this system is invertible, the convolution of these two impulse response must give you the impulse function. So this is the invertible property. And furthermore, for the causal systems, if an LTI system is causal, if and only if the impulse response is a causal signal. So the system is causal if the impulse response takes zero values in the negative time domain. And this is the definition of a causal signal. Right? So that's why we define this causal signal in this way. So we can say that the LTS system is causal if the impulse response is a causal signal. And this is because when if the impulse response is causal, then first of all, again, we can write down the input and output relationship of the LTS system. Now, this is just a standard convolution. But now we know that this signal is zero in the negative time domain. So basically, when we consider this integration, the range for tau can be truncated at t. Because if tau is larger than t, then inside this H, we only have negative time domain. So that this time will be negative. And in the negative time domain, the impulse signal is zero, and that contributes zero to the entire integration. So we can basically restrict the integration up to time t. And this means that the output only depends on the present input and the past inputs. By definition, that means the system is a causal system. Because now the integration is up to t. So this integration only involves x tau, while tau is up to t, up to the present time. So the output only depends on the present and the past of the input, meaning that the system is causal. And if for this causal LTS system, right, if the input signal is also causal, and then the input and output relationship can be further simplified in this way. So the integration can start from zero instead of negative infinity, because now the input is also causal. So looking at the input signal in the negative time domain is meaningless. So basically, we can look at the causality of the impulse response to determine the causality of the LTS system. And moreover, to examine the stability of the LTS system, we can look at the integrability of the impulse response signal. So if the LTS system is stable, an LTS system is stable if the impulse response is absolutely integrable. That is to say, if the impulse response can be integrated in this absolute sense, then the LTS system must be a stable system. So this provides another convenient way to examine the stability of LTS systems. And you can see that all these different types of system level properties can be examined by looking at the impulse response only for LTS systems. So that's why the impulse response is really the fundamental characteristics of LTS systems. Okay. So before we go to the graphical interpretation of convolution, are there any questions regarding the this part. The input and output relation between of the LTS systems.
When you were talking about the stability, so that's when, is it both the input and the output are bounded?
So recall the definition of a stable system, right? A system is stable if the following happens. Now, if we feed a bounded input signal to the system, then the corresponding output will also be bounded.
Okay.
So that is the definition. And this is argument for proving this statement. Basically, for LTS systems, okay, so we can look at this one. Now, suppose we feed a bounded input. The magnitude of the input is bounded by B to the system. And now let's look at the output, the magnitude of the output of this LTS system. First of all, by the input and output relation of LTS systems, we know that YT is the convolution between X and H. So this inside is just convolution. So the magnitude of YT is just the magnitude of this convolution. And then here we are just doing a change of variable. Yeah, I believe we just do a change of variable. So now we have H tau and XT minus tau, just a change of variable. So after that, we know that this is a standard inequality, which means that this inequality means that the integration of a product, the magnitude of the integration of a product of two complex signals is less than or equal to putting the magnitude inside. The intuition is that inside you can have positive or negative numbers, they may cancel out. But if you put the magnitude operation inside, everything will be non-negative. So that will give you a bigger result. And then we know that the input is bounded by B, so we can replace this part, the magnitude of X, by capital B. So this is less than or equal to capital B integration over H. So therefore, in order for the output to be bounded, we can require this integration to be bounded. And this integration is only involves the impulse response. So if the impulse response can guarantee is absolutely integratable, meaning that this integration is finite, then the output is guaranteed to be finite. And in turn, that implies the stability of the system.
Okay, thank you.
Yeah, so you can see that the impulse response really provides a very convenient way to understand the fundamental properties of an LTS system. Okay, any other questions?
Not related to the lecture, but have you let us know when the midterm is going to be?
The midterm one?
Yes.
Yeah, you can find the information on the canvas. I mentioned that in the beginning of the course, so it's going to be on the next Tuesday.
Oh, okay. Thank you.
And let me know if this time does not work for any of you, so we can schedule a separate appointment. Okay, so now we have convinced ourselves that to understand this LTS system, we need to look at the impulse response of the system. And in particular, once we have the impulse response, the entire system input and output relationship can be analytically characterized by the convolution operation. So, so the question is how to understand this convolution operation. So here we provide a graphical illustration of this convolution idea. So this is the input and output relation of LTI system. Right? So xt is the input signal, ht is the impulse response. Now yt is given by the convolution of the two in this way. Now we can see that inside this integration, we are taking integration over tau, right? The integration is over tau. So the variable that changes is the tau, and t here is a fixed time index. So we are looking at the output signal at the value of the output at a specific time t, and this value is calculated in this way. So here t is a fixed constant, and tau is really the time variable. And we can see that in this integration, to evaluate this convolution, to evaluate this integration involved in the convolution, we need to first understand these two signals, right? And one of them is just the input signal x tau. Right? Again, here tau is the time variable. T is a fixed time constant, time index. Okay, so so this is the standard. This is just the input signal x tau over the time variable tau. And this h is different. It is kind of reversed because we have negative tau here, and also shifted because we have time offset t. So to generate this signal, we need to first flip the impulse response h tau backwards in time. So this is basically a time reversal operation. Right, so we need to, from x tau to ht minus tau, we need to first do a time reversal to get h negative tau. So this is a time reversal operation, and then we do a time shifted to the right by t. That will give us t minus tau. So this is the basic signal operations that we talk about in the lecture 2. Specifically, this is reversal, and then in order to generate this t, positive t, I need to introduce a negative t inside. And this is basically replacing tau by tau minus t, meaning that after the time reversal, we need to shift the time reversed signal to the right by t units. So that gives us the ht minus tau. Okay, so basically we have the input signal, and for the impulse response, we reverse it and then shift it to the right by tau units. After that, we can do the multiplication of these two signals, right? So, and then once we have this product, in the end, we do the integration over tau to get yt. So this is a example how to illustrate how the convolution process applies. So basically, we have the signal, input signal x tau. Now suppose in this case, we are looking at a rectangular input signal x tau. And we are also given another rectangular impulse response signal h tau. So to do that convolution, right, we need to first generate ht minus tau, which means we need to first for the H tau signal, we first reverse it, so flip it to the left-hand side, and then shift it to the right by tau units. After that, we will multiply this signal pointwise with the input signal and calculating and doing the integration over the entire time domain. And because the integration is over, in the integration, the variable tau is changing. So which means that this signal ht minus tau is being shifted from the left-hand side to the right-hand side. Because the range for this tau ranges from negative infinity to positive infinity. So intuitively, you can imagine that we are fixing the input signal x tau here, and we are moving the impulse. Now this is ht minus tau, which is the signal shifted. Yeah, sorry, this is shifted by t, not tau. Okay, so the signal is h tau, so the time shift here is actually t. Okay, so basically, if you want to look at the value of the output yt, you want to look at the output value at a specific time t, you need to generate this shifted ht minus tau with that specific t. And then you do the multiplication between the input and this ht minus tau, taking the integration over tau. The value of the integration gives you the value of yt. And then in the next lecture, we'll talk more about this. If you want to look at all the values of yt over t, so once you vary this value of t, it is like you are shifting this ht minus tau from the left to the right. And through that process, intuitively, these small rectangles now convolving with the big rectangle from left to the right. And depending on their overlapping area, the value of the convolution will change from time to time. So in the next lecture, we will go through this process in more detail. But you can take a look at this illustration figure by yourself first. Okay, so I will stop here, and we'll see you next Tuesday. And I will take office hours after this over the Zoom.
Thank you.